Hi everyone, this is the model answer for the specific heat capacity higher question. Figure 1 shows a kettle a student used to determine the specific heat capacity of water. The student placed different masses of water into the kettle and timed how long it took for the water to reach boiling point. The student carried out the experiment 3 times. The student's results are shown in the table below. So we've got what looks like quite a complicated table to start with. We've got our mass of water down here. We've got the 3 repeats for the time for the water to boil, and then the mean or the average. Then they've got the mass times the change in temperature, and then they've calculated the energy supplied in kilojoules for the end column. The first question says, suggest how the student was able to ensure that the change in temperature was the same for each mass of water. Okay, so for this one, the first thing would be to say that water boils at the same temperature each time, which is 100 degrees. So water boils at the same temperature each time. And also, what they would also need to do is control the starting temperature of the water by allowing enough time for the water and the kettle to reach room temperature before they started it again. So control the starting temperature by allowing the water and the kettle to cool back to room temperature. And because of those things, the student can ensure that the change in temperature is the same for each mass of water. So same starting temperature and same end temperature. So for the next part of the question, it says, calculate the uncertainty in the student's measurements of time to boil when the mass of water was 1.75 kilograms. So we're going to have to go back to our table here, and we're looking for 1.75. Okay, so there we go. We have got 3 readings, but the mean is missing. And I'm going to write those 3 readings down. The first one is 298 seconds. The next one is 300 seconds. And the last one is 302. Okay, so in order to work out uncertainty, what we need to do is we need to do the range of the data. So work out the range of the data, and then we need to divide that by 2. So uncertainty equals 302 minus 298. Divide that by 2, and it gives us an uncertainty of plus or minus 2 seconds. Okay, so every reading that is in that table has got an uncertainty of plus or minus 2 seconds. The power rating of the kettle is 2.2 kilowatts. Take note of that, we've got a kilowatt there, kilowatts times 1,000. Calculate the average electrical energy used by the kettle in kilojoules for 1.75 kilograms of water to reach boiling point. So for this one, we need the equation energy transferred equals power times time. Okay, so here I've got my power, which is 2.20 kilowatts. Now, because I want an answer in kilojoules, and that's given in kilowatts, it means that I'm actually okay and I don't need to do a conversion at this point. I do, however, need to find out the time. So I need to look for 1.75 kilograms in the table. So here I've got my 1.57 kilograms. And I need to use the time. Now this is why the average is missing. So that time it wants there is the average time. So if I do 298 plus 300 plus 302, then divide that by 3, I will get 300. That is my average time. So the calculation I need to do is 2.2 times 300, and I will end up with 660 kilojoules. Question D. Use information from the table above to calculate the change in temperature of the water during the investigation. Okay, so for this one, what you need to do is you need to be quite clever. You are looking for change in temperature. So if you have a look in your table here, you've got mass times change in temperature. If you divide that by a mass, then you'll just end up with change in temperature by itself. So the calculation we need to do is mass times change in temperature divided by the mass. But it needs to be the right pair of values, so the same pair of values. So what I'm going to do is I am going to use the first one because it's there right in front of me. I've got a change in temperature, a mass times change in temperature of 20, and that's paired with a mass of 0.25. Now you could have used any pairs of numbers as long as you're using them as a pair. So my mass times change in temperature is 20. My mass is 0.25. If I work that out, it gives me 80 degrees C. So change in temperature of the water during the investigation is 80 degrees C. For question E, we also need to have our table near us because it's asking us to complete this graph. So the student plotted a graph of energy supplied in kilojoules against mass times change in temperature. They've started this graph, but they want you to complete it and plot the 4 missing points. So let's have a look. What I am wanting to plot on my graph is energy supplied and mass times change in temperature. This is our x-axis and this is our y-axis. They have done all the way to 60. So we've done that one, and that one. I need to complete this. So I need 80. And I can see there that I'm going up in hundreds. So each little square is a 10. So 80 is paired with 401. So I've got 80. I'm going to go up to just slightly over 400. Using a little cross. Sharp pencil would be nice. The next one is 100, and that's 471. So 100 is 4. Sorry, the 20 is 20, 40, 60, 71. That's my fault, sorry. Every little square is 20. 20, not 10. The next one is 120 and 587. So it's 5, 20, 40, 60, 87. And then we have got some points there that we can plot on, although we have got the last one that is missing. So we need to work out the energy that's being supplied in kilojoules. So to do the last one, we need to look back at our calculations from earlier. We've already worked out that the energy transferred is power times time for the 1.75 kilograms of water, which is the one that's missing. So the 1.75 kilograms of water, the missing value is 660. So that's the point that we need to put on the graph now. So 140 is 620, 40, 60. So you actually got something that looks like quite a nice straight line graph. And that's our next task. So the next thing that we need to do is get our ruler, and we need to do quite an accurate line. This one is a straight one. Not always in science do we have straight line and best fit, but this one is straight. One thing I will mention is not all lines of best fit go through the origin, and this one does not go through the origin. Okay, so I'm going to do my line of best fit like this. So we've got a nice straight line there. And that's handy for us because in the next question, we need to use this line of best fit in order to work out the gradient. So use the graph to determine the mean value of specific heat capacity of water for the student's investigation. So from maths, in order to do a gradient, it should be the change in y divided by the change in x. Or you might know it as rise over run. Okay, so for this question, what we need to do is we need to find a couple of nice points so that we can draw a nice little triangle through them. So that one looks quite nice there for me. And I'm going to draw it up to that point there because it goes straight through it. So this will give me my change in y, and this will give me my change in x. So I'm going to work out my change in y first. Okay, so reading across, I can see that my first value is 220 and my second value is 660. So it's 660, take away 220, and that should give me my change in y, which is 440. And then I need my change in x. So let's see where I've gone from. That value there, which is just slightly beyond 40. So I'd say that's probably about 42. And I've gone up to 140. So my change in x is 140, take away 42, which gives me 98. Another thing that I need to just bear in mind is that the energy supplied is on the graph in kilojoules, and I need it to be in joules. So when I'm doing this one, which is the energy supplied, it's 440 kilojoules. To convert that into joules, I times it by 1,000. So 440 kilojoules equals 440,000 joules. And that is my value for changing y that I'm going to use. So gradient equals 440,000 joules divided by 98. If you get that into your calculator, 440,000 joules divided by 98, that gives me 4,489.8. Okay, now they have given you a range. You are allowed any number in the range between 4,200 and 4,800. Okay, so that it's quite a big range, but it does depend on the accuracy of your plots and whereabouts you've put your line of best fit. Okay, key for that one to remember is the conversions. This is in joules, this is in kilojoules. You'd only notice that if you read and looked at the units there. So make sure you're clearly looking at the question each time. Okay, so for the next bit, the student's value for the specific heat capacity of water was greater than the accepted value. Suggest why. Now, there's always a question like this that's added on after you've done a specific heat capacity question. And it's because some of the energy that is supplied does not actually go into raising the temperature of the water. Right, at this point, it's not really good enough to say that some of the energy is wasted. But some of it would go into raising the temperature of the surroundings or raising the temperature of the kettle. But for you, for this question, it would be good enough to put some of the energy does not raise the temperature of the water. So the temperature hasn't gone up by enough really, because not all the energy has gone into it. And then with the last question, question H. The kettle used in the experiment had a label stating that the power rating of the kettle was 2.2 kilowatts. The student did not measure the power of the kettle. Suggest why measuring the power of the kettle may improve students' investigation. Okay, so just because it says it on a label doesn't actually mean that its power is exactly 2.2 kilowatts. So what she would have to do is measure it, and then she could accurately calculate the amount of energy supplied. Okay, so the power of the kettle may not be 2.2 kilowatts. Okay, it might be slightly under or maybe slightly over, or they might have rounded it. So the knock-on effect there, by measuring power, the student can accurately calculate the amount of energy. Calculate the amount of energy. Okay, so well done for completing that question, guys. Some of it was a little bit tricky, but I'm sure you've done absolutely fine. Please email me if you've got any questions about that. I'll be happy to get back to you. Thank you.